Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. So students, today we are going to discuss about the module Separator materials for Redox flow batteries from the paper Energy Related Materials. So students, let us see what are we going to study in this module. First, what are the commercial membrane materials? Secondly, we will be discussing about the properties of commercial membrane materials. Thirdly, the modified membrane materials. Next, we will be discussing about the ionic conductivity and the chemical stability of the membrane materials. Lastly, we will be discussing about the transport phenomena in a RFP. So let us start with a brief introduction about this module. A perfect membrane or separator materials must prevent the mixing of electroactive species of the electrolytes flowing in the anolyte and catholyte sites and the direct chemical reaction of active species which can result in energy losses. Now, the permeation of the active species and the selectivity of the charge carrying ions throughout the separator is highly important. Typical separators for RFP are IEM, which are fabricated from the polymeric materials with the pore diameter of about 20 angstrom. In aqueous electrolyte, the IEM, they are designed to conduct the positively charged ions or negatively charged ions by means of cationic and anionic exchange membranes. In a recent paper on lithium ferricyanide flow battery, a solid electrolyte separator is utilized to transport these lithium ions from reaching to the negative electrode. The ideal membrane for the RFP should be chemically resistant to aggressive species and it should exhibit the low area resistivity to minimize the ohmic losses. The ion exchange capacity is often used to measure the charge carrying ions passing through the membrane, and the conductivity of the membrane is determined by various factors such as thickness, ionic group concentration, the degree of cross-linking, the size and the valence of the counter ions. Although the transfer of the vanadium ions through the membrane was found to be highly dependent on the concentration difference between the positive and the negative electrolytes, the cation and the anion exchange membranes tend to have net volumetric transfer through the positive and the negative compartments respectively. Compared to an anion exchange membrane, the cationic counterpart tend to have lower area resistance per thickness due to higher mobility of H plus ions compared to the anions such as SO4 2-. This explains the fact that a cation exchange membrane is the most widely investigated membrane material for RFP. However, the chemical stability of different IEM could vary from each other depending on their chemical structure. In general, the IEM based on perfluorinated backbone, particularly the Nafion cation exchange membrane from DuPont USA, they have superior chemical stability to the most types of hydrocarbon membranes. However, recent studies suggest that AEM could effectively reduce the crossover of vanadium ions in VRFB due to the Tonen exclusion effect, which is an electrostatic repulsion between the cation groups within the membrane and the electroactive species. Commercially available membrane materials. Perfluorinated membranes have been commonly used in RFPs due to the high conductivity and good chemical stability in the oxidizing electrolyte. These membranes have been commercially available as the following trademarks, that is Nafion from DuPont USA, Flemion, Asahi Glass Japan, Fumapem from Fumatech Germany, Esiplex from Asahi Chemicals Japan, and Dow Chemicals from USA. In comparison to the other materials or hydrocarbon type cation exchange membranes such as Selimion, CMV, DMV from Asahi Glass, Nafion membrane has superior chemical stability in the vanadium electrolyte. Furthermore, through Nafion membrane, vanadium active species can permeate, which decreases the Coulombic efficiency. The diffusion coefficient of vanadium ions across the Nafion membrane has been determined to be in the order of, that is V2 plus is greater than VO2 plus, which is greater than V3 plus. The commercial membranes have good selectivity and high ionic conductivity, including Nafion 112, 117, and 324. These are all from DuPont USA. K142 from Asahi Chemicals Japan, Selimion 1 CMV, CMS, AMV, DMV, ASS, DSV, Flemion CMF, New Selimion Asahi Glass Japan, and RAI R1010, R4010 from PAL RAI USA. Despite this huge transport of electroactive species from one compartment to the another has been observed with all these membranes. In spite of these membranes discussed above, properties and cycling performance of the other commercial 15 membranes have been evaluated by Vefius and Skylus Kazakos for the vanadium bromine RFP system. As observed from the table, the properties of these membranes are compared with the properties of Nafion membrane from the literature. Although Nephion 117 and Hippor are thicker than the others, they have smaller area resistance and larger permeation of V4 plus ions have been observed. Also, higher area resistance was observed with the high IEC membranes such as the ABT membranes than those with a low IEC such as Gore and Hippor membranes. These suggested that there is no direct correlation between the thickness, IEC, resistivity, and diffusivity. Among these membranes, only Nephion, ABT3, L01854, and M04494 were reported to have acceptable performance in terms of round-trip DC energy efficiency and chemical stability. Since all the other membranes degrade very fast in the vanadium-bromine electrolyte, the cycle life has been limited to less than 40 cycles. So students, now we will discuss about the modified or composite membrane materials. As we have already discussed that Nephion membrane has a high ionic conductivity and good chemical stability in an oxidizing electrolyte. However, the high permeability of active species across the membranes still remains a major challenge for RFBs. Hence, the transport of electroactive species through the membrane need to be hindered for better performance of RFBs. Hence, in order to improve the ion selectivity and chemical properties, Nephion membranes are required to be modified as hybrid or composite membranes using certain organic and inorganic materials such as poly,4-vinylpyridine, polypyrols, polyaniline, polyethyleneimine, that is PEI, polyvinylidene fluoride (PVDF), polydimethyl ammonium chloride polyanion, polysodium styrene sulfonate, that is PDDA-PSS, silicate SiO2, organically modified silicate, organic silica modified titanium oxide, and zirconium phosphates. These membranes are often synthesized by electrolyte soaking, oxidation polymerization, electrodeposition, in situ sol-gel, or impregnating methods. Regarding the high cost of Nephion membranes, some developments have focused on the modified or composite membranes based on non-Nephion or other non-perfluorinated separators for VRFP. Early approaches includes the modification of low-cost separators such as Daramic and low-density polyethylene LDPE by grafting and sulfonation processes. The table summarizes the various developments which have been focused on the modified or composite membranes based on non-Nephion or other non-perfluorinated separators for VRFB. Although the resulting membranes have high IEC and conductivity, the diffusion of active species through the membrane is still significant. Therefore, it has been suggested that polymerizable monomers might be grafted onto the matrix of polyvinylidene fluoride or PVDF. One example is polyvinylidene fluoride graphed polystyrene sulfonic acid, which can be said as PVDF GPSSA PMAN as tabulated, where MN is the maleic anhydride used to reduce the irradiation dose to the membrane. The PVDF GPSSA PMN was observed to have good chemical stability and low ionic permeability in vanadium electrolyte. Further increasing of the grafting degree could lead to higher water uptake, IEC, and conductivity, which is clear from the table also. As with polyvinylidene fluoride, other polymer matrices such as sulfonated polyallyl thioether ketone, that is SPTK, and sulfonated polytetrafluoroethylene or SPTKK have been investigated. These have been tabulated also. Due to the electrostatic repulsion between the cation group of the membrane and the soluble species, AEM tends to have lower permeability than their cation counterpart membranes. Typical AEM can be synthesized by chloromethylating a polymer substrate with chloromethyl ether and then quaternizing an amination reagent such as trimethylamine. Early modified anion exchange membranes based on polysulfone PSF and polyphenylene sulfidesulfone PPSS have been suggested. However, the IEC of this membrane is still less than that of Nafion 117. Therefore, some researchers suggested the grafting of dimethyl aminoethyl methacrylate DMAEMA, an anion monomer, onto the ethylene tetrafluoroethylene ETFE and PVDF films by UV-induced grafting. Now, due to the low ionic permeability, sulfonated polyether ether ketone, that is SPEAK, has been used as the substrate for the Nafion SPEAK composite membrane. A thin layer of Nafion 1 was used to prevent the degradation in the electrolyte, while diamine was used to cross-link the sulfonic groups of Nafion ionomer with the SPEAK ionomer. Many investigations have been made to blend the SPEAK membranes with PTFE, tungsten oxide, SiO2, sulfonated polyether sulfone, and polysulfone 2-amide benzimidazole (PSF) ABIM to reduce the permeability of vanadium ions across the membranes. To enhance the performance of RFP systems, novel sandwich type membranes such as sulfonated polyether ether ketone, that is SPEAK, or tungstophosphoric acid TPA, polypropylene PP, and sulfonated polyether ether ketone SPEAK perfluorosulfonic acid PFSA acid TPA, polypropylene PP composite membranes have been introduced. These sandwich-type membranes consist of a layer of polypropylene membrane which is sandwiched by the two layers of SPEAK or TPA membranes. Due to the sandwich design, the battery can operate for longer cycles even when the external layers are detached or out of function. Hence, with such structured membranes, the RFP system results in improved round-trip DC energy efficiency and permeability in an all-vanadium flow battery. PTFE reinforced SPEAK or PTFE composite membranes were reported to have low water uptake and swelling ratio compared to pristine SPEAK membranes. The VRFP single cell assembled with SPEAK or PTFE membranes showed larger coulombic efficiency and energy efficiency and longer cycle life than that with SPEAK membranes. Other low-cost separators consisting of sulfonated polyphenyl sulfonate membrane and sulfonated polyarylene thioether (SPTK) have also been evaluated, but long-term stabilities in vanadium electrolytes need to be further investigated. Recently, it has been reported that polyacrylonitrile nanofiltration membranes could enhance the efficiency of VRFP, making them a more viable tool for large-scale energy storage. Now here the idea is based on tuning the vanadium proton selectivity via pore size exclusion, which gives a totally new concept in the design and the preparation of the membrane separator. Properties of the membrane materials. First property which we will be discussing is the ionic conductivity. The ion conductivity of a membrane describes the ability to conduct the protons or the anions in both directions during charge and discharge in order to balance the charge differences between or which are occurring during these reactions. Since the ion conductivity of such a polyelectrolyte determines partly the resistance and the voltage drop inside the electrochemical cell. A suitable polyelectrolyte needs to have a sufficient ion conductivity in order to achieve a good performing and efficient redox flow battery. The ion conductivity of a polyelectrolyte results from the fixed charge groups on the polymer backbone of the membrane. So, according to the charge of the fixed groups, the ions are transported through the ionic domains inside the membrane. Fixed negative charges in the ionic domains will promote the conduction of positive charges, that is cation exchange membranes, and positively charged fixed groups will promote the conduction of negatively charged ions or the anion exchange membrane. Not only the ionic conductivity needs to be reasonable, but it also the crossover of the reactive species through the membrane need to be low to avoid the self-discharge. Cases are reported in such a Nafion membrane resulted in a lower or equal energy efficiency compared with the lower ion conductive membranes. Now students, next we will discuss another property of the membrane materials, that is chemical stability. Now during charge in the positive half cell, a RFP produces ions which have a very strong oxidizing potential. Since these ions are in its highest oxidation state, it will act as an electron acceptor to fall back in the more stable oxidation state. Furthermore, for example, in the case of VRFB, the vanadium solution needs to have a high acidity due to the poor vanadium solubility in neutral solution. The membranes applied in the vanadium redox flow battery or VRFB need to be chemically stable at these harsh conditions. Many pathways have been described in the literature to enhance the chemical stability of IEM for other type of energy conversion and storage systems like for fuel cells. Although the stability issue of membranes for various RFB systems was noticed by the scientific literature, it never was picked as a major topic in order to quantify and understand the degradation pathways. Even though VO2 plus is claimed mostly as the major degradation agent, other states like V2 plus might also have a high degradation potential since it is a very strong reducing agent. Finally, to the best of our knowledge, no scientific work has been done on the long-term stability of polyelectrolytes in contact with such strong reducing agents as V2 plus. The majority of publications on VRFBs deals with the application of first sulfonated perfluorinated polymers, second partly sulfonated fluorinated polymers, as well as third sulfonated polyarylenes with conjugated bonds. For the latter, here we mention sulfonated polyether-ether ketone as an example. The sulfonation of the precursor polymer will also sets the limits to the stability, whether it is chemical and mechanical. Little work has been done in the field of anion exchange membranes as compared to the amount of work done on cation exchange membranes, mostly sulfonated polymers. As per the literature review, only a few AEM have been prepared and tested for the RFP application. In conclusion, a suitable material for the RFP, it needs to be stable in the electrolyte and it should have low crossover for electroactive species. Also, more work needs to be done on the chemical stability of polyelectrolytes for RFPs in order to understand the degradation procedures to be able to engineer a cheap, conductive but stable membrane for this promising energy storage application. So students, the next property which we are going to study is the ion permeability. The transport rate of active species across the membrane will determine the coulombic efficiency of the cell and the capacity loss with continuous charge-discharge cycling. A standard test procedure was developed by Scalis Kazakos and the co-workers to eliminate any interference from water transport due to osmotic pressure effects across the membrane. For example, in VRFB, the vanadium ion permeability measurements typically involves the measurements of the diffusion rate of vanadium 4 ions across the membrane from a 1 molar of VOSO4 and 2 molar of H2SO4 solution on one side to a blank 1 molar MgSO4 and 2 molar H2SO4 on the opposite side using the UV visible spectroscopy. MgSO4 is used in the blank solution in order to balance the osmotic pressure of the two solutions and eliminates the effect of water transport across the membrane. So students, let us summarize what we have learned from this module. Perfluorinated membrane have been commonly used in RFPs due to the high conductivity and good chemical stability in the conducting electrolyte. These membranes have been commercially available in the following trademarks: Nafion from DuPont USA, Flemion from Asahi Glass Japan, Fumapen from Fumitech Germany, Aciplex from Asahi Chemicals Japan, and Dow from Dow Chemicals USA. In comparison to the other hydrocarbon type cation exchange membranes or CIM such as Selimion CMV, DMV, Asahi Glass, Nafion membrane, they have the superior charge chemical stability in the vanadium electrolyte. Nafion membranes, they have a high ionic conductivity and good chemical stability in an oxidizing electrolyte. However, the high permeability of active species across the membrane still remains a major challenge for RFPs. Hence, the transport of electroactive species through the membrane needs to be hindered for better performance of RFPs. Hence, in order to improve the ionic selectivity and the chemical properties, the Nafion membranes they are required to be modified as the hybrid or composite membranes using the organic and inorganic materials such as poly,4-vinyl pyridine, polypyrols, polyaniline, polyethylene amine (PEI), polyvinylidene fluoride (PVDF), polydimethyl ammonium chloride, potassium polysodium styrene sulfonate (PDDA or PSSA), silicate, organically modified silicate, organic silicate modified titanium oxide, and zirconium phosphates. Thank you.